I'm a bit switch gears to talk about more kind of a theoretical formalism. So I'll talk about this non-equilibrium function approach to this energy transport and the momentum transport, which is related to Casimir effect, as well as the angular momentum. So my talk will be kind of roughly two parts. The first part is essentially the non-retardation limit, namely the speed of light goes to infinity. So that is essentially the Coulomb interaction. And in the second part, we talk about the full electromagnetic interaction. So I would like to advertise a formula known as Wingreen formula. And this formula was actually in this electronic transport and used many times. But I think that we could actually use this also in the context of either near field interaction or Casimir force. So the advantage of that is that we could go beyond what the people usually use in fluctuation electrodynamics. In other words, the system could be intrinsically in a non-equilibrium situation. So in that case, this Meir Wingreen will be useful. So here is kind of the model that I talked about. So let's imagine that you have a bunch of electrons hopping on the lattice or maybe some arbitrary structures. So the idea is that let's separate into two parts so that the electron is not allowed to hop to the other side. So in such a situation, although they are not connected, electron cannot go to the other side, but they can again still transmit energy because you have a Coulomb interaction. So the model is such that you take kind of a bunch of leads. So this is the left lead, is right lead, and so they have a Coulomb interaction only when they are close. So the lead itself has no Coulomb interaction because the screening causes the free electron to be a very good model. So this is one of the lead. So here is the Coulomb interaction in second quantization notation. So if you ask how much energy is actually transmitted from left side to the right side, and you actually take the rate of change of this Hamiltonian with respect to time, and here you need to be careful. This average, this non-equilibrium average, and this time derivative are not commuting. So you have to actually take this time derivative first, then you take the average, and then you let the lead go to infinity. So basically, you have to have a bus which is infinity so that you can supply an energy. And the Meir Wingreen actually derived kind of a similar formula, but the original Meir Wingreen is for the electron transport, but it's very easily generalized to the energy transport. But there is a distinction between heat and energy, but in this case, it's the same because the electron cannot go over to other side, so it doesn't really matter. So this could be identified as energy or a heat, which is equal. So this is an exact formula, meaning that if you solve this problem exactly, you actually get an exact result. So here there are two things. One is the Coulomb function for the electron, that's G, and the sigma here is the characterize the interaction between the between the central part of the electron and with the lead, and so we call it self-energy. So how do we solve such a problem? In fact, there is no exact solution. There is a formal solution, but there is no exact way of doing this. So here I'm actually using one of these popular approximations. So basically we say, okay, there are two classes of diagrams. As far as the electron is concerned, there are the Hartree term that give you this lollipop diagram, and then this electron circular photon interaction. So this is the Fock diagram. So this part is the self-energy that is for the electron that goes into here. So this sigma n is for these two diagrams, and this sigma L sigma right is for the connection of the center with the lead. Then you also have this I call it scalar photon, but it's actually the Coulomb interaction that you can rewrite in the following way. So you have this unscreened Coulomb, which is a little which is the previous formula that is here. And because of this interaction, you got extra term. So this extra term is the polarization diagram that is this this one, pi. So this is a kind of a Dyson equation. So we have an expression for these two terms. For example, if you just use this kind of a Lewis order approximation, you get this G times G, and this self-energy is G times G. And so if you can use this as a kind of a approximation to this problem, you can actually rewrite this formula approximately into an alternative formula. So in this alternative formula, we completely eliminate the presence of the electron and only talk about this scalar field or photon field, and that has the alternate formula. So I would like to emphasize this formula because this formula can be generalized in the other case when you have a real photon. So, based on this, we can do further approximation that is the so-called local equilibrium. So in the local equilibrium, you say that the fluctuation dissipation is valid. So in the sense that this pi lice is related to the Bose function and the real part part I and part A. So this result, when you say it's valid, so then you get an alternate formula, and that is the Landau formula. So in the Landau formula, you have this difference in the Bose function. So the difference between here is that here you don't have to be in local equilibrium, but here you already assume that it is in local equilibrium. Okay, here is a kind of calculation based on Landau formula. So we did two calculations. One is based on the type binding graphene. So basically, it's only nearest neighbor model hopping on a graphene lattice with a hopping parameter that is the standard value of 2.8 and only nearest neighbor. So this is calculated between two graphenes. One sheet. One is 300K. One is 1000K. Then we give a chemical potential of 0.1 eV, and but here's another calculation that is much more sophisticated because this calculation is based on the first principle calculation. So what you need to do is to do the density functional theory to get your electronic structure and optimize the structure, and then you run this Berkeley GW, which is kind of a way of calculating this pi in my formula. So both of them are non-local calculation. So in other words, this pi actually is a function of both positions, and also in k-space, of course, it's k-dependent. Because we use unit cell, of course, we are in k-space. So basically, both of them has a very similar feature. So the saturation, when your distance is very close, quite close, the actual value differ a little bit. And also the slope is 2, or close to 2 numerically, and here it's more close to 2. And so basically we confirm that indeed we have this long distance has one more square chemical-dependence, and then it's saturated. So we hope that this first principle calculation can be generalized to some more general situations that you really don't need to have a parameter. It's actually completely parameter-free calculations. So another kind of calculation that we try to, the motivation for this calculation is this experiment by Capizzo. And so in that experiment, it was identified that this heat transfer is 7 times larger than the theoretically would allow, according to Electrodynamics. So what I'm doing here is let's try to have a toy model. So the toy model is that let's take a one-dimensional chain, but with the end, that end can have a Coulomb interaction. The rest are not allowed to have any Coulomb interaction. So what we do is let's increase the size of this and make it say this is a 1 by 1. This may be 3 by 3. So in other words, take a blob of kind of a 3-dimensional kind of wire, and we see what is the heat transformation. So if you take 1 by 1 block, something like this, you get extremely large value in terms of heat transfer normalized by this area. In other words, I take the actual total heat divided by A squared. So that is the normalization. That the reason for that is we try to compare with the parallel plate result. So if you increase this 1 by 1, 2 by 2, and the consequence is that it decreases. And eventually, when you get to infinity by infinity, which of course we calculate in k-space, and you get much smaller, so you decrease by maybe 3 or 4 order magnitude. So the lesson we learned here is that the screening is very important. So basically, if you have more of those, they actually screen, so they actually decrease. But if you can allow them to non-screen, so you have some tape that is actually exposed, so it cannot be screened, then in that case, you should get larger values. Okay, here is kind of a different kind of a system that is the top one. Here is the graphene. The graphene actually, if you cut them, you can have two geometries. One is a zigzag, one is armchair. So we use zigzag. The reason for zigzag is that the zigzag has kind of a surface state. The armchair has no surface state. So if you use zigzag, you actually get quite large contributions for this heat transfer. And here's a kind of a graphene sheet you cut into kind of a tape. And again, you can actually see a contribution. So what we found here is that if you put this in a dielectric, you know what, if you have background dielectric, it actually enhances the transmission. So a higher dielectric can give you a higher value. In fact, the peak actually shifts to the a further distance. And the distance here is only several nanometer scales. Another thing that is really beyond what the fluctuation electrodynamic could do is that we could make the system non-equilibrium by driving them with a current. So here, in this model, we have a top graphene and a bottom graphene. So in the bottom graphene, we actually drive them with a current. So because we drive them with current, they are no longer equilibrium. So we cannot really use the standard fluctuation dynamics. But it's almost the local equilibrium is still in some sense works in the sense that when you drive them current, you can show that if you assume something we call a kind of Baim-Einstein, meaning that this d less, sorry, it should be d less, not g less, not d less. That's wrong. So this is the nearly in equilibrium except this f function. This f function is not the equilibrium function, but kind of a non-equilibrium version of it. In principle, you should solve Boltzmann equation, but we don't do that. We actually use the circle mode relaxation to mimic the non-equilibrium situation. So if you use that, you find that this distribution actually switch over to kind of an alternative distribution is essentially the Doppler shift. So you can Doppler shift this distribution, but the conductivity is not calculated by Doppler shift because that's not quite correct. So we actually have to calculate the conductivity anew in this framework. So the interesting in this system is that even if you have equal temperature between top and bottom, and if you drive the bottom, then there was a heat transfer, even the temperature are the same, which is not against the second law because they are not in equilibrium. So if you drive them, if you increase the temperature of the top, and this decrease, and eventually a reverse sign because this becomes much hotter than the other side. Okay, the second part is about a more general theory. So in the more general theory, setup is the following. So you have kind of some arbitrary piece of materials. When I say material, in my mind, I'm using metals. Basically, each one of them are actually a tight binding model. Then you have to have one more that I call infinity because in this case, the edit can transmit, so I will identify the outside as one more piece of the object. So I actually have n plus one an object. So we want to ask what is the energy transmitted among them, and what is the force applied and torque applied, which are these three conserved quantities that we can ask. So the basic framework is this non-equilibrium grain function. So what you need to do is to define a quantity that is running on the not the real time, but on the contour time. So what is this contour time? This contour time actually, you start from minus infinity, go to some larger value, come back to the infinity. The reason for that is when you evaluate some Heisenberg operator, and usually you have this forward, backward. So each of those time tau actually representing two times. Not only you say where you are, but also say which branch you are. So plus branch, minus branch. So that gives you four different kind of grain functions. So the basic observable, of course, is the A vector potential. And so we are using a so-called phi equals 0 gauge or temporal gauge. So this is the basic quantity that we need to compute. And this gives you kind of four different kind of grain function, time order, anti-time order, less than greater than. They are not completely independent. They have some relation just based on the definition. And what is actually important is this retarded one, which is related to linear response, and also the last one, K, which describes the distribution of the photons. Okay, in fact, let's take a more careful look. So you have this greater and less. So greater, when it's greater, you put A in the order as in the argument, but in the case of less, you switch the order, and because the operators are not commute, and these two are different, and the difference is actually give you the retarded component of it. And if the system is in equilibrium, then you have the fluctuation-dissipation theorem. The way that I put it in this way, maybe they don't look like the one that you see typically in fluctuation dynamics, but it's actually equivalent. And Ricardo gave a very nice article on this fluctuation dissipation. And you can say that this is the fluctuation dissipation of the first kind, because it's talking about fluctuation dissipation of first kind or fluctuation dissipation second kind. There are two equations that is quite important in this framework. One of these is the so-called Keldysh equation. One of the is Dyson equation. And in fact, the original one is the Dyson equation. So if you do perturbation, you found that you actually have a Dyson equation. But that Dyson equation is defined on the contour. So this Dyson equation, when written in this way, is actually the contour version. But the contour version is equivalent to two versions. So the last one, the retarded one, and the retarded one is essentially the Dyson equation. But if you write this Dyson equation out explicitly, it's nothing but it's essentially the Maxwell equation in this framework. So the material property comes in this pi here. And so this pi is essentially linear response respect to the field A. But this A is not external perturbation. So this A is the actual field that is go here. That's why this is a pi, not psi. So the Keldysh equation describes distribution. As I said that we have an environment. So this environment gives you one additional term that is not calculated according to the material property, but actually in some sense calculated by boundary condition. In fact, it's actually implied in this contour order, the Dyson equation. And if you solve that, in fact, you get one more term, and this one more term is identified with the so-called self-image of vacuum. So in other words, each of the pieces of the body has a pi, and including the one that is outside, we call it environment. And if you assume the environment is also in thermal equilibrium or in local thermal equilibrium, and we have this fluctuation-dissipation theorem as well for that quantities. Okay, I need to make a comment about this the gauge that we have used, because we are using a particular gauge, and so this gauge is you just put the scalar field phi to 0. And that is known as axial gauge or double gauge, and that is actually commonly known in quantum field theory, but it's not in condensed matter physics, because in condensed matter physics we usually use transverse gauge. And the reason is that the transverse gauge is easy to quantize, and this gauge is not so easy to quantize. The reason for that is that this equation that is relate this current to the A don't have a Coulomb's law. The Coulomb's law do not appear here. So as a result, when you quantize it, the Coulomb's law has to be enforced. So this enforcement causes little technical problems. But from an energy point of view, it seems to be okay. It's not a problem at all, because normally we don't really need to know exactly what is the state that goes into here. So the notation that I have here, there's a little bit here. It's actually just the same as the dialectic Green function that is usually used in the fluctuation dynamics. And the quantization, of course, is the standard quantization that goes here. And if you are in the transverse gauge, you have to use the so-called transverse delta function. But here is the normal delta function that goes into it. So next topic is to talk about how do we calculate the quantities observables, and we calculate the NH transformation, which is the Poynting vector Poynting theorem. And because U is a finite, so the average and time derivative actually is commute. And because they commute, if you take the average, this is 0. So basically, you have two ways to calculating this. Either you calculate the Poynting vector, or you calculate the volume integral. But as we will see, that the volume integral is much better. So in addition to this Poynting vector, we also look at the the angular momentum transformation and this momentum transformation. So we have kind of a similar kind of a conservation law. So this conservation law tell you the significance of that. So basically, you have to have this Maxwell's tensor, and in the other case, you have to cross with R, and that is the angular momentum part of it. So these three equations give you kind of a uniform kind of a formula that is nearly the same. The only difference is that you have to take a time derivative or space derivative. So you can write the energy current is related to the geoheating, of course, and the force is originally this Lorentz force. However, we don't like to have a rho because we want to get rid of rho. So we get the rho by continuity equation, and then we can, because we are in steady state, so we actually can do integration by part. So based on that, we can actually take the force and write everything in terms of A and G, and the torque is kind of similar, except that you have to cross product with this R. And so the difference between this force and the torque is that you got an extra term. So that extra term we interpret as a spin contribution. You have an angular momentum, orbital angular momentum contribution that is here, and the spin contribution. If you go back to this formula, you see that the right-hand side is always G and A, some combination of G and A. So the vector field A and the active current. So in fluctuation electrodynamics, you divide the current into two terms. So one is the induced current, one is the fluctuation current. But in my formulation, this is the operator. So this is the total current. So because the presence of that, you found that this combination is very important. So I defined a new function called F. And this F, let's sum them over all. So this F depending on which object we are talking about. So if you sum over all, you can show by equation motion method, you can show that this F is just d times pi. So that means my system is closed. I just need to talk about two quantities. One is pi, one is d. So I can formulate everything in terms of these two physical quantities. But one thing I need to, in order to talk about what is the transformation among these different objects, I have to use so-called additivity. In other words, my total pi for my whole system is the sum of the contribution from each piece of it. And that is not rigorously correct because you always have a higher order term that break this additivity. I will show you the diagram. So once you have this one, you can use this so-called Lagrange rule to look at this greater and less because that goes into the formula. So that give you RK and KA kind of a term. Okay, let's talk about this additivity. So if you make kind of a Feynman diagram expansion to the lowest order, it's just this bubble diagram. But you can also go to a higher order. So if you go to the sixth order, in a sense that it has 6 vertices, then you get this diagram called a Slasmos-Lacan diagram. And that diagram you cannot write as a sum of 2. So in other words, if this is alpha and this is beta, and they are not sum, they are multiplied, they are not sum. And in fact, this diagram has some consequence. For example, this is one of the important diagrams when you calculate Coulomb drag. So additivity is assumed, which means that I'm going to ignore the possibility of such a diagram. So let's take a kind of a simple situation that the interaction is just A times G. So with this, we have again kind of a Dyson equation, and we have kind of explicit formula for this diagram. So basically, you need the Coulomb function of the electron. So this gives us kind of a computational recipe. This pi, if you use local approximation, it's actually just related to conductivity and dielectric constant. So this is the standard relation between our notation and the more common notations. Okay. So using this relation, we can have kind of a very general formula. So this formula, they look different, but actually they agree with old formula by Krieger et al. 2012. And also 2 days ago, I saw a poster, and this poster actually gave a formula that is for the G, for the angular moment part. So I haven't really checked the details, but I believe that they are actually completely equivalent. So basically, you need to have this total angular momentum, which is the orbital part plus spin part, and that gives the contribution to the torque. Okay, that's the theory part. Let me go to some of the results. I guess I will skip this. Okay, in order to calculate some kind of a concrete result, I'm going to make further approximation. So this further approximation is that I'm interested in small molecules, so I assume that the screening is not very important. So I will take this big D approximately equal to the non-interacting one, this free function. And then I also do the multiple expansion, meaning that because my system is very small, so I expand around this R equals 0. So I have this monopole, dipole, and so on. So if I do that, I get this, if I take kind of a small cluster of molecules, so I get a formula, and it turns out that this formula is same as the Fermi-Gordon rule. So if you do the Fermi-Gordon rule, you get the exact same formula. As for the torque and the force, if you average over, you need to do this surface integral. So if you average over the angle, you get kind of a formula that is directly related to pi. And so this is the formula that we actually use to do the actual compilation. Okay, let's take a look at some of the calculations. So here is kind of a benzene. You take a benzene molecule. So this benzene molecule is modeled as 6 sides hopping around. So you won't expect angular momentum because it's completely symmetrical, but if you drive them with a current by actually attach a kind of a lead unsymmetrically, then there will be more current going here, less current going there. In other words, you break the left-right symmetry. So by drive them, in this case, you indeed see a current. So, but this current turned out to be mostly 0 unless this bias is such that the kind of jump from this this state to the other state. So this jump over here causes this high kind of a peak. Here is kind of a profile that goes through this. So so this is kind of a non-equilibrium situation because the system is driving by current, so the system is not in equilibrium. So the last example here is graphene. So in the graphene here, we also drive them with current. So basically, we take a semi-infinite graphene with an edge. In actual calculation, actually we have two edges. It's kind of a strip. So when you drive them, the system is out of equilibrium. So in this case, do we actually see angular momentum and the force? The answer is yes. You do see. Certainly, of course, you have kind of a energy, but this because of the effect of the edge, you also see in kind of angular momentum radiation. So let's focus on this plot. So this plot is actually you plot 3 quantities. So how much power you have generated, and how much force torque you have applied, and how much force you have. So this is the order of magnitude. So so what we do is that we have to bias them. Unfortunately, we have to bias them with very large bias, perhaps too high to actually melt them. So, but anyway, this is kind of a theoretical calculation. So, so if we bias them with a high bias, indeed you generate this 3 quantities. Maybe the other plot is kind of a better plot to look at. So, what you see is the first column is the power. The second one. Second one is the torque, and the third one is force. And the top one is zigzag, the bottom is armchair. So if you change the orientation, the detail actually change. So that means that these effects are really due to the age effect, because if it's positive effect, it shouldn't change with the different kind of orientation. And so what you have seen is the horizontal one is the chemical potential to the right, and this vertical one is chemical potential to the left. So this is kind of the bias, the intensity with respect to the bias, and they are sort of complicated because it depends on the hopping between different levels. We expect that the surface state should have some rule, but if you look at it, actually they don't show up. Somehow the distinction whether you have surface state or not didn't show up on this calculation. Okay, here I want to summarize a little bit. So the theory is fully quantum mechanical. Whether the system is in equilibrium or not, whether the system is reciprocal or not, it's exactly the same theory. So I'm thinking about maybe it will have some advantage when they are in a strong coupling. For example, if we put the system into a cavity, and then of course you change this V. And another thing is that if the system are very close to each other, then this pi should be determined self-consistently. So in that case, it could be that the left property of the left is really dependent on the property of right because of this coupling in this theory. And we also can do first principle calculation. We'll try in that direction. But there is kind of a drawback. The drawback is that because we work in real space, so we have to work on small systems, or maybe sometimes we use periodicity, we could work in K-space. Another thing that bothers me is I cannot do moving objects. So if the object moving, I don't know how to formulate this. Okay, let me account my groups. Yongmei did some angular moment calculation, and Zhu Tao did the first molecular calculation, and Zhang Zuxi also did the molecular calculation. Okay, I'm stop here.
Thanks for the nice talk. Questions?
Thank you very much. It's a good theory. So just a question in terms of what Chanhui Fan is doing with chemical potential of photon. Do you use chemical potential of photon?
No, I'm not using that, because the way that I set up is that I have a piece of material. I put explicitly the electron chemical potential on the left, electron chemical potential on the right. So in the middle is determined by the Green function. So the chemical potential do not show up.
But your
for the photons.
Yeah, the functions are non-equilibrium, right?
Yeah.
And the distributions is photon distribution is non-equilibrium.
The photon distribution is indeed is not in equilibrium, but it may or may not be able to write as in that form. But I don't explicitly look at this. They come out by solving this Dyson equation numerically. So I'm not writing that. But if you take a kind of a semiconductor kind of a situation, I believe they will come out naturally. Okay. But it's not in the theory by putting it by hand. It's coming out of the theory.
I see.
Yeah.
Okay.
You showed these results for heat flux between two plates of graphene. There are, of course, also calculations from fluctuation electrodynamics. Did you compare your results with these results, and do they agree? And should they agree?
Because our theory is a non-retardation limit, so for short distance, we expect they agree. And for long distance, of course, you get a contribution which will be flat out, so they will not agree. So our theory, so we expect it to be valid around 1 nanometer to 10 nanometer regime. That will be the dominant contribution.
Okay, but you did not compare yet.
Exclude comparison, no. Yeah.
Any other questions or comments? Actually, I have one question.
Yeah.
So, have you thought about extending to retarded regimes and how one would go about that?
Yeah, if you follow the second part of this, it's nearly the same formula, except that your matrix is originally is a number, now become a 3 by 3 matrix. We haven't really did the actual calculation, but our theory should be able to do that. But the difference is that in the scalar one, in the non-retardation one, we are looking for the charge-charge correlation. But in the second part, we need to do the current-current correlation, which is a more difficult calculation.
Okay, thanks.
Just one quick clarification. So you mentioned that you put phi equal to 0, and then you have the vector potential there. So is this vector potential quantized in your formalism?
Yes, the vector potential is quantized because we need to calculate the vector potential Green function. Only the quantum theory can have a well-defined Green function because we need to commute them or not commute them. So only the quantum theory can do that. Okay. The only problem with that is that if you use the normal quantization, you can write this A in terms of a creation and annihilation operator. But in this theory, if you still try to do that, then if you apply the A to a kind of a vacuum, you generate a state that is physically not allowed. In other words, you have to enforce the Coulomb's law to the state. And that is a technical problem when you look at this state. But in NEGF, we don't actually look at the state. We look at, we say, okay, we start with something that we certainly know, which is the vacuum, which is a little way. Then we solve this Dyson equation. So somehow that problem don't seem to appear in the formalism. In the quantum field theory, it does have a problem.
Thank you.
Yeah.
Thank you. Can you go back to the angular momentum emission from benzene?
This one?
Yeah, the previous.
Previous one.
So are each of the carbons in benzene at a different local equilibrium, or is it the whole molecule?
These molecules are not real molecule.
Yeah.
This molecule is just a quantum state.
Okay.
So it's a tight bonding model.
Okay.
Yeah.
And so can you extend this calculation for to what system sizes of your site? You have this 1 through 6 sites. Can you extend this for slightly larger?
If you do it numerically, the maximum that we can do is about the Saurin. So if you have a Saurin site, if your matrix is Saurin by Saurin, we can do it. Beyond Saurin, it becomes too big to do.
Okay, thank you.
Yeah.
Any other questions or comments?
So in your heat transfer calculation, you calculate all the way to 1 angstrom, right? 10 to the minus 10 meter.
Yeah.
So in that case, so I'm wondering whether you have phonon interaction or heat conduction instead of photon interaction.
Certainly, if it's actual distance, electrons start to tunneling. You soon trust the result, of course. But we do have a calculation that is take into the possible tunneling. But if you take about the possible tunneling, then you have to use, then you have to go back to the other formula that I did in this very beginning. So basically, if you allow the tunneling, you cannot use this formula anymore. You need to go back to that formula. That formula allows you to handle the possible tunneling. In fact, I have a kind of calculation. I didn't have time to look at. So
in your next slide number 6, yes, you have the result.
Okay, this one. So what I want to say is that forgot to mention that. you see that if you take the infinite plate, you get this result. But suddenly they swoop up very drastically, and that's because we have put in kind of hopping between this left to right, according to this exponential form of hopping. So basically, you allow them tunneling. So tunneling produce a huge kind of a contribution to the current. But we don't have a phonon, so our model has no phonon at all.
Yeah, thank you.
Any other questions? If not, let's thank all the speakers again.